Today it is lecture number 20, and here I will talk about marginal protein mass function and conditional protein mass function, and in together we will go to discuss how to calculate all these how to calculate all these. Also how it helps to understand or how it helps to calculate joint PMM protein mass function. So first I would like to discuss about marginal protein mass function. What is that? So it is one kind of if you are having random variable x and y with respect to a given random experiment, then just finding the uh, protein mass function of x only. That means finding the protein mass function of any random variable in isolation leads to marginal protein mass function. So that kind of concept I will discuss. So what is that? The joint protein mass, we have already gone through that. The joint protein mass function, it provides information about the joint variable x and y. So here notation would be joint protein mass function. That means uh, that notation for joint protein mass function is pxy of xy. That means it is function of two variables. If you are having two random variables, so generally it is talking about joint behavior of any two random variable x and y, and we are also interested in the probabilities of event involving each of the random variable in isolation. That means we are also interested in the situation where x is in isolation. Separately we will deal x. So in order to discuss separately x, that protein mass function we are calling it marginal protein mass function, and we denote that protein mass function by px of x. Similarly, for the random variable in isolation, we will denote the corresponding protein mass function by py of y. Py of y. This is the situation. Okay. This can be found in term of marginal protein mass function as follows. So how we can find? So just go to definition of protein mass function of a single random variable. Remember that marginal protein mass function happens to be protein mass function of a single random variable. So suppose you are just right now at the moment you are dealing with x. So how can we define protein mass function for x? And here x is discrete in nature. Right now I have already told that I am discussing here discrete protein mass function. So uh, easily we can get a countable pattern in the range of corresponding protein in the range of in the corresponding random variable x. That means omega x easily we can put in a countable fashion because omega is a discrete set due to discrete random variable x. Okay, due to definition of discrete random variable x. Okay, so from there we can easily put the point of this omega x in the form of a sequential order. So that sequential order we are in a single sequence. That sequential we denoted by xj, where j is coming from subset of natural number or natural number. Simply, I would like to call it natural number. So it is always nice to proceed with indexing with starting indexing 1. So this is the scenario. So 1 xj if you are taking, then how we define protein mass function for that xj? It is equal to, it is saying that it is the probability that x is taking value xj. The random variable x is taking value xj. Okay, and further what you observe that same thing you can relate it here, like you are taking a event a from the sample space, then this sample space also you can represent it like this way: a union anything from the sample space, anything or any b or whatever is, so anything from the sample space union wise. So it is not going to affect the happening of a, it is not going to affect you are talking about. So from that perspective you can say that x equal to j and y equal to anything, y may be anything here. So that perspective is coming. So it is talking about the union perspective. That means probability that x equal to xj and y equal to y1 union. That means you have to take all possible value of y. So from that perspective, so if you try to observe this probability mass function of random variable x, it is taking up this infinite union of probabilities. And in simple, what you will observe that if you try to convert this one because this one, what is this, if you just focus on this, so this is nothing, it is talking about joint probability mass function for x and y of where x random variable x is taking value xj and random variable y is taking value y1. And what is happening, you can observe that this event is independent of this event, and likewise vice versa. If you take in this union any two event, that would be independent in nature. So it will leads to just summation of the corresponding probability mass function, summation of corresponding joint probability mass function with respect to second argument y, because you have taken y here anything, so it is directly coming from this scenario. So if you are having any event, then that event also you can write as a union b. It is not going to change anything while calculating probability. Or a union, simply also you can say that a union sample space, anything in sample space generally. So a, what is a equal to a union sample space, you can write it like this way. Or no, sorry, from there just you need to apply the de Morgan's law or famous theorems from state theory. You can say that if you want to write from state theory perspective, then a, you can say that a union uh, sorry, a intersection phi, and likewise, if I'm saying that what is A union phi, A union phi, it would be phi itself. So these are very simple property of set theory. You can derive all these. In class 12th, you might have already seen such kind of things. So from that, so I'm taking this scenario. This is this scenario. A intersection, and is always talking about intersection. So A intersection sample space of phi, or sample space omega, or you can say that if you're talking from the event value of random variable perspective, you can say that this intersection y is taking anything, then y taking value from the sample space of y, that means omega y, it is taking value from omega y. So due to that, you can write it like this way. And if you observe things closely, so you are taking summation with respect to second argument yk. So that's way here what you do, you can observe that how you can get marginal probability mass function of a random variable x. You do marginalization of y in the joint random variable of x and y. This is the joint random variable x and y, and you do marginalization with respect to y variable. That means you are taking summation with respect to all y variable. So that's why y will be exhausted, it will be finished, and now remaining thing would be just it will talk about probability of x only. So due to that, we are defining marginal probability of x. Similarly, we can define marginal probability of y. How? Go in the same pattern, because here I have taken always we are used to of that when we are having two kind of random variable or even two variable jointly, then always we used to take first variable x as a first coordinate and y as a second coordinate. That's where this convention I have taken. So here suppose this marginal probability mass function of y is defined by probability that y is taking value yk. Now, what we observe that we will again use the same condition, that we know that a is equal to a intersection phi. So from that perspective, we can say that here x can be in joint variability x and y. Here x can be anything. So if you are taking anything, then if you take x with respect to each separate value of x, this would be independent with respect to this one. That means this would be disjoint with respect to this one. So likewise, so just if you take it together all these, it is just talking about marginalization of x. So marginalize x in this joint probability mass function, then what remaining thing you will get? You will get a marginal probability mass function of y. So this is the scenario to get marginal probability mass function of respective random variable from the given joint probability mass function. So I will take few example. So this example you have already seen that. So what is the calculation perspective? I had already mentioned that calculation of marginal probability mass function from the joint probability mass function we can do if that domain is very, that sample space is very small. in case of discrete random variable, it always happens to be a small. So, and suppose there are only two kind of random variable x and y, then the corresponding joint protein mass function of the random variable, you can put those finite number of value in a two-dimensional table. So, one example you can observe here like this way, and in this table, what you do, if you do row sum, then here you can see that along x-axis you have taken value of first random variable x, and along y-axis we have taken second random variable y. So x is taking four value 1, 2, 3, 4, and y is also having four value 1, 2, 3, 4, 5. So and all these are the value of joint protein mass function. Now from this given joint protein mass function, how we can perform marginalization? So if you do row wise sum, that would give marginal probability distribution of y, because if you do row sum, rows has been exhausted. Now columns, just we are getting a single column row, all the rows sum has been converted and collected into a single column. If you do row wise sum, then you are getting a single column, and this column, it is talking about protein mass function of what variable y. So that protein mass function we are calling it marginal protein mass function of y. In the similar fashion, if you do column sum of all these columns, so first you sum it up. So sum would be 3 by 20. If you sum here columns, if you perform column sum of this joint protein mass function, then sum would be 6 by 20. Here in third column, sum would be 8 by 20. In the fourth column, sum would be 3 by 20. So this row, so if you do perform column sums, so those column sums will be aggregated to a single row. So you are getting a single row. This single row is talking about marginal protein mass function of x. So this is the scenario through which you can calculate marginal protein mass function from given joint protein mass function. One example. This example we had already discussed before. Another example here I have taken. Suppose you perform a random experiment that is dealing with rolling or tossing two dice. So you know in dice there happens to be in each dice we observe six number of outcome. Either it would be one, or either it would be two or three or four or five or six. So in total, you can easily define joint protein mass function. Uh, Here joint protein, these are the joint protein mass function, easily you can define. So it is suppose if you are not able to define, just right now consider it joint protein mass function is given to you. So here first random variable x is taking 6 value, it varies from 1 to 6, that means 1 2 3 4 5 6. Y is taking all these value. Now here you are having you are fine with joint protein mass function of uh, this experiment, that means tossing two dice together, and due to that you are getting this joint protein mass function. Okay, now what you do from here, question is that first find what is marginal protein mass function of second variable y. So in order to get that, y is taking value along vertical axis, so that's why you have to perform row sum. If you sum all these this row, this sixth row, what would be summation? Summation would be 1 plus 1 plus 1 plus 1 plus 1 plus 2. So that means 5 plus 2 7, 7 by 42. Similarly, if you sum fifth row, what is the summation? So 1 plus 1 plus 1 plus again it would be 7 by 42. Keep on summing. So that summation of rows, it will give your marginal distribution of y, or marginal protein mass function of y. So again sum 1 plus 1 plus 1 plus 2. Again it is 7 by 42. Now here things are coming 1 plus 1 plus 2 plus 1 plus 1 plus. So again 7 by 2. So here 1 plus 1 plus 2 4 and plus 3 7. So 7 by 20 in with respect to third row. If you sum all the entries in the third row, 7 by 20. If you come to here, it would be 1 plus 2 plus 1 plus, again it is all these are coming 7 by 42. All are equally distributed, equally likely. So every value of y having equal probability. So here again you sum it up, it would be 7 by 42. Okay, and what you observe? So this marginal protein mass function, you got it. It is taking value 7 by 42. When y are taking y, it is taking value, what are the possible value of y? Possible value of y is either it will be 1. Why is talking about when you are tossing second time, the outcome in the face what your number that appears, that we are calling it. So in dice, either you will get 1, or you will get 2, or you will get 3, or you will get 4, you will get 5, or you will get 6. So likewise, so these are the possible value of y. You won't get, if you toss a roll a dice, you won't get other than these 6 digit. Okay, so otherwise value of this protein mass function would be this 0. Otherwise, someone can claim that I will, when I will toss a uh, dice, and it would be 1.5 and 2.5 or something like that, or 8 or 9 or 7. Such scenario is not possible. For those scenario, the value of protein mass function would be 0. So that's scenario. So you got the marginal probability for marginal probability mass function for y. In the similar fashion, you can get marginal probability mass function for x as well. So how you can get that? So for that, you need to do summation of columns. So two columns of sum it again. So what would be 2 plus 1 plus 1 plus 1 plus 1 plus 1? So it would be again 7 by 42. Likewise, if you sum second column, so second column would give summation again. Summation would be 7 by 20, 7 by 42. Likewise, even sixth column, sum of sixth column, it would be also 7 by 42. So you got the marginal probability distribution of x as well. So what is the formula for marginal probability distribution for x in this experiment? Formula is we are denoted by probability mass function of x is equal to 7 by 42 when x is taking value any one of 1, 2, 3, 4, 5, 6. So in that case, the value of probability mass function is 1 by 42. Otherwise, uh, x will have probability mass function 0, because we don't observe when we toss first time that dice, we don't observe uh, 1.5 or 2.5 or 7 or 8, something like that. We just observe these 6 digit only. That means either it would be 1, or it would be 2, or it would be 3, or it would be 4, or it would be 5, or it would be 6. So these are the possible outcome when you toss dice first time. So these are the possible output. That means these are the possible value of uh, x, random variable x. Otherwise, protein mass function will take 0 in other scenario. So this is the marginal. These are the marginal protein mass function that we got from given joint protein mass function. So always such kind of problem will come. You all have to be enough smart in order to solve problem. So sometime what will happen? I will give joint probability mass function. You have to find marginal probability mass function. Also, in next part, I will discuss about how to find conditional probability mass function. One more problem it is given here. So just note down this problem. It is just for your practice. You can solve this problem. Then that means finding joint probability mass function of a discrete random variable. Here again, it is a process of finding joint probability mass function of discrete random variable. I will cover this problem once I will discuss in detail about conditional probability mass function. That after that I will discuss this. I am coming to conditional probability mass function. What does it say? So definition again I am recalling. Suppose we are having a probabilistic model, and we are told that we know some partial kind of information regarding that probabilistic model. That partial information we are saying that it is A. One event A is already occurred in a probabilistic model. So if A is already occurred, so our new universe would be with respect to A. So whatever new, we will try to observe new kind of event, or if we are going to calculate probability of new kind of event, or if we are going to define any kind of random variable, then we will try to calculate probability mass function of that random variable with respect to the partial information A or the event which has already occurred. From that perspective, we will try to calculate. So that's why our universe has been changed. It is no more our universe is a sample space, complete sample space. It is just whatever partial information we are having, that would give a new universe. So from there, so you can simply say that we are putting a conditioning over the random variable by a event A. That means that by a partial information A or by a some kind of information A. So that kind of thing. So we can capture this knowledge by employing the conditional instead of original probabilities. So here, if you want to calculate probability distribution of random variable, we can't use elementary probability, or simply we can't use probability mass function. So here we have to use the term of conditional approach. So conditionally we have to go to find distribution of a given random variable with respect to partial information. So in order to do that, the conditional probability mass function of a random variable x condition by or condition on the random event A with the positive probability. That means A definitely it is a possible event. It has the event A. That means we are definitely know about that partial information. That one is a possible event. It is not like that. It is the given information is impossible kind of thing. Given information would be always possible kind of thing. Then we will define conditional probability mass function. How we can define it? So in order to define conditional probability mass function, we have to look back to definition of conditional probability. So again, I used to say that this conditional probability mass function, generally you can denote it by px given y of x, or you can also define like this way: px given y of x given y a. Is your partial information. So this is your conditional probability mass function. This we define with respect to what? With respect to probability that x is taking value small x given the partial information A. And we know that either you can call from the value of random variable perspective, you can say that it is one event. So we can talk about this conditional probability is nothing, just it is ratio of joint probability of x equal to x and A divided by probability of A. This is the definition of conditional probability mass function, and you can go into simple sample space as well. So you, here we don't need that in a detailed perspective. If you try to look from the geometrical perspective, the definition of conditional probability mass function, that condition is coming from a event A, we can observe like this way. So that means initially, if you don't have any information regarding that random experiment, then we are saying that this complete circle, it is this is containing information of all possible events of the corresponding random experiment. But someone is saying that now A is the event that we know about that. That means we are having some partial information regarding sample space. That's that A. This is A. So we are having information about A. So once we know that A is already occurred, that means we are having information about A. Then how we can find probability mass function for other value of x? So where you are taking x equal to x, so that random variable capital X, it is taking a small value. So it will talk about intersection. We will try to look into within A. We won't worry about what is happening outside A. Within sample space, what is happening outside A and what kind of value this small x is taking, we don't have to worry about. Just we have to worry about that how much content of x is there in the given information A, how much content. So you can observe from pictorial, you can observe that this X, it is taking this much of information within A. Within A, this much of information. So definitely we will say that the probability for this X, conditional probability for this X would be larger than this value of X dash. So X dash is taking very little information. X dash observe very, it is having very little information within A. So A is giving very little information regarding X dash. So that's why we can say that conditional probability mass function for X dash, it is very small in related to conditional probability mass function of X. Why? Because X is having more information than X dash in A. So what A is your the partial information which is already given provided to you. So all these things. So you can also say that the probability of A that you divide it, it is a normalizing constant. From the pictorial things, it would be much more clear. So note that the experiment that or event in the random experiment, it is always a random variable which is taking a particle value. Always you can call that one is a specific kind of event. So it is an event. So it always disjoint are disjoint for different value of A. So that concept I had already discussed that if you are taking values of random variable and if you map it back to sample of space, then the value of discrete random variable always define a what partition in the sample space. It is the very inherited property of discrete random variable. It is not happening with continuous random variable, but it is happening with discrete random variable. So that's where that criteria is taking. That means if you take any two separate value of a random variable, then you can say that those two events would be totally disjoint. And there, if you uh, take their union, so if you take their union in A, then that union it would be in because each value of random variable happens to be mutually exclusive. So it is very easy to define union just by summing up or by taking union, disjoint union. So you can take like this way. That's why it is very easy to calculate probability of the given information A. So it would be just summation of this conditional probability, summation of this conditional probability, summation of this that value of x probability that value of x which falls in set A. So to do this summation over x, that would give probability of A. And if you generalize it for x for every value of the random variable, then it will lead to what normalizing condition. That means conditional probability mass function is also satisfying normalizing condition. That means summation over all the value of x, it would leads to equal to 1. Let x, so one example here I would like to take. Consider x with the roll of a dice. Okay, so this is your experiment here. What is you are rolling a dice, and a with the event that roll is an event, and x is random variable that you are defining. That whatever outcome you observe while tossing a rolling a dice, so that would be x. So x is a random variable, that means number that appears on the face. So x will take six value. Either it will take one, or it will take two, or it will take three, or it will take four. Likewise, or it will take five, or it will take six. So x can take six possible values. These are the possible value of x. Okay. Now, here partial information is given that A with the event that roll is even number. So A, what are the even number in this rolling of a dice? So even number happens to be 2. This is 2 is even, 4 is even, 6 is even. So these are the outcome in A. So we know about this outcome, this outcome, even number, even number. We know about this one. Then based on this given information, what would be the conditional probability mass function of x? So conditional probability mass function again we will define from the all these are coming from the definition. So I just I'm putting it in a very layman way. So I would like to say that conditional distribution of x given A, it would be just the ratio of that probability that x is taking value a small x and x is even, because x must we have to look within A. We don't have to look outside A. How much of x is within A? So that we have to look. So that's why this joint probability is coming here. Joint probability divided by probability of even. So how many even we observe? 3 even. So one situation I have already discussed several times. Don't go and calculate number of events in the denominator separately and number of events in the denominator separately. Directly calculate how much of x is happening in A. So that calculate. So here if you are taking x equal to 2, so how many 2 you observe in A? Just 1 2 out of 3. So that's where probability that conditional probability mass function for x equal to 2, it would be 1 by 3. Similarly, how many 4 you observe in A? So 1 out of 3, 1. So that's why Protein mass function for x equal to 4, it would be 1 by 3. Again similarly, protein mass function for x equal to 6, it would be 1 by 3. Otherwise, if you take any odd number, that would be not in a, or any odd number, it would be not. You can see that here there is no odd number in a, so a is not giving any information regarding odd number or odd number outcome. So that's why for that case protein mass function will take value 0, so otherwise it is 0. So the scenario is already given here. So one example of how to calculate conditional protein mass function. Now, conditional one more conditioning is there. So last case we had discussed about we can put conditioning over x by some event. So now here what we do, here we can put conditioning over a random variable by another random variable. So it is a little bit generalization of last case. So what we do, suppose we are having two random variable x and y, both are associated with the same experiment, and suppose we know that the experimental value of y is taking some particular value y, a small y with the probability, positive probability pxy of y greater than 0. So that means we know we are having information about this one. So that is the partial information. So this partial information will provide partial knowledge about happening of x. So how much happening of how much what is the probability that x is happening in together with y once we have already observed y. So that probability we can calculate with the help of conditional probability. So definition you can observe it here. This knowledge it can be captured by the conditional probability mass function of x given y of random variable x, and where y is already given. It can be defined with the help of this definition. Again, this definition when I have already mentioned, then when capital P is coming there in the definition, always consider that as a probability, and that means it is dealing with elementary probability what we have already covered in model 2. So here this is probability mass, conditional probability mass function, and you can say that it is abuse of notation. Actually conditional probability mass function we are defining it like this way: probability of x given y of x given y. So we should read like this way, but sometimes just abuse of notation. We know that here only x is varying. We are worrying about at a particular time y is fixed, so it is actually function of x only. That's with this notation might be fine if you want to proceed further. So there would be no issue. So it is defined by this formula that probability that x is taking a particular value x given y have already taken a small y value. Okay, so so it is simply a conditional probability, and conditional probability again we have to look back to definition of conditional probability. From there we can define it like this way, and finally we can observe that the conditional probability defined like this way: the ratio of joint probability of x and y divided by marginal probability of y. So remember that you have already observed y, that means this number is fixed. So if someone is asking that, can you say anything about the plot or nature of graph of conditional probability and joint probability? Who would like to give answer? Okay, Sriram, would you like to give answer? What is the relation between shape of conditional probability mass function and joint probability mass function? Sriram Shiv Ganesh, do you see any relation between the shape of conditional probability mass function and joint probability mass function? Not. Don't know. Okay, it's fine if you don't know. I told that here in the definition of conditional probability mass function, this quantity is what? It is fixed because you know about y. You have already observed y. So that means it is known to you. You know it will take some value between 0 and 1. So due to that it will treat as a constant, and so you can say that the this conditional probability mass function and this joint probability mass function both will have similar kind of shape. Both will have shape. If it is Gaussian, then this would be also Gaussian. If it is binomial in nature, this would be also binomial in nature. So that scenario is coming. So both the shape of conditional probability mass function and joint probability mass function always happens to be similar to each other. So that is the concept. Further, this function of x, so the same thing I have already written here. and we are calling this denominator probability normalizer as well. And we can also say that this conditional probability mass function satisfy normalizing criteria. You can easily verify all this. So it is satisfied because it would be constant. So it would be summation. Just you are taking summation with respect to this x, and that will lead to 1, okay, because of this conditional approach. So easily it satisfy conditional probability mass function also satisfy normalized condition. So one pictorial visualization we can see it here. So suppose for each fixed y, you view probability mass function along the slice y equal to y, and we re-normalize so that you can observe that. So if you are taking y equal to 3, then what are the value of joint protein mass function? If you are fixing y equal to 3, so you will get this height, this height, this height. That means you are just walking along this row. So these are the possible value of joint protein mass function. So if for each for a single fixed y, this value, this height, if you sum it up, summation would be not 1. Why? Because it is not giving a distribution of value of random variable. But how we can get a distribution? So here x is varying, so we need to normalize it. How we normalize it? By dividing the probability that y is taking value 3. So if you divide all these height, this vertical bar, with the probability that y is taking value 3, then you are getting this one. So you can easily observe that this height is relatively smaller than this height. We know that probability. So here this conditional probability mass function, that x of x given y of x given 3, it is defined as ratio of joint probability of x and y. Sorry, y would also come here. X comma y, joint probability mass function of uh, x is taking any value, any arbitrary value, but y value is fixed. That one is taking 3. So divided by value of marginal protein mass function of y, that y is taking value 3. That is defined by. So easily you can say that this one is a fixed number, and this number is a probability. It will be always less than 1 and greater than 0. It is a positive number which is less than 1. So if you divide some number which is less than 1, then the resultant would be always exceed, it will be greater value. So that's why you can observe that if you divide this by this probability, then it will height, this height has been increased. Further, if you divide it by probability of y taking 3, it has been just increase similar like this way. So if you take in the similar fashion, if you take y equal to 2, fixing y, then this probability would be normalized to. So you can say that this has been normalized to this has been normalized to this, and this height has been normalized to this, like this way. Similarly for y equal to 1, it has been normalized to this, and you can observe that shape is, relative shape is not changing. So relative shape is not changing. This one is you can observe that in this joint probability, this one is the highest bar. In the similar fashion also in conditional probability mass function, we observe that the highest nature of same thing for x equal to 2, it remains the same, it is not going to change. And you can observe that these two are relatively smaller. So here also we can observe in conditional probability these two are relatively smaller. Here likewise, here also we can say that, see that this is the highest bar for y equal to 2. Then we can observe that the corresponding bar in conditional probability is also, this one is the highest one, and this one is the second highest. That's why this one is the second highest, this one is the least one. So that's why we are getting least structure. So we can see that a very interesting map or one-to-one correspondence between the size of conditional protein mass function and size of joint protein mass function. Okay, it is already 45 minutes. Around 45 minutes regarding attendance. Put your roll number there in the comment box, and if you have any question, then you are welcome. Otherwise, I am going to wind up today's lecture.